second part of our double header, you should realize that our speaker really had to brave the elements and work very hard to get here. Mike's flight into Frankfurt was canceled. He went to Berlin. He just got here this morning. So he has really worked very hard to get here. Our speaker, as those of you in computer science surely know, is the legend of databases, the winner of the Turing Award in 2014, and also a number of years earlier of the IEEE von Neumann Medal and other honors as well, Mike Stonebraker.
Good morning. Lufthansa is high on my shit list right now. But other than that, I'm delighted to be here. What I'm going to talk about is big data. This is going to be the absolute opposite of the talk you just heard. This is going to be a huge mushy field with what I think is worth working on and what I think is not worth working on. So I'm going to talk about big data. Mostly the interesting things about big data are about disruption, because that's when the established vendors get faked out by the new guys. And then I'm going to talk about the 800-pound gorilla in the corner, which is the thing you really should be working on. Okay. So what's big data all about? Well, it was invented by a marketing guy for some company maybe a decade ago. And it doesn't mean anything it means whatever the marketing department wants it to mean. What I'm going to say it means is that you've got a big data problem if you've got one of the three V's. Either you've got too much data and you can't manage it all, or it's coming at you too fast and your software can't keep up, or it's coming at you from too many places and you have a horrible data integration problem. So I'm going to talk about each of the three, and in the big volume, I'm going to talk about, well, if you want to do SQL analytics, you want to do stupid analytics on a lot of data, that's one problem. And if you want to do more complex analytics on a lot of data, second problem. Okay. If you want to do SQL on petabytes of data, there are a bunch of commercial vendors. I know of maybe 20 or so installations that are running in production with multiple petabytes of data on very, very big clusters. And in my opinion, as a research problem, this is the definition of it's solved, which is there are plenty of commercial offerings. Just for example, Zynga, the game company, the guys who wrote Farmville, Zynga records every click anywhere in the world in real time and use that to have their marketing and engineering folks figure out how to sell more virtual goods. The real business model of Zynga and Farmville is to convince Chinese teenagers to impress their dates by buying more virtual goods. Anyway, if you want to do SQL, I don't see it being a big research problem at this point. And everybody runs the same architecture that's been pretty much proved to be the right way to do it. They're all running multi-node systems that are partitioned. They're all parallel column stores. If you don't know what any of that means, go look at Vertica, go look at Presto, go look at Hive. They all work roughly the same way. Do not go look at Oracle. Oracle doesn't run this way. Oracle is nowhere in the warehouse business. So anyway, there's no gorilla here. And there's only really two flies in the ointment that I see in the data warehouse world. The first one is all the data warehouse products were built either a decade or more ago. I built one of them. And we all were optimizing for network bandwidth. That was the high pole in the tent. Try and save sending bits around between the nodes in a partition database. Well, the problem is in the last 10 years, network bandwidth is increasing faster than CPU main memory bundles are getting beefier. So alas, current data warehouse products and systems deployed are not network bound. So anybody who does research on saving network bandwidth in a data warehouse world, forget it, it's not worth it. It's not the high pole in the tent. So this is going to cause a re-architecting of commercial data warehouse products, and the engineers are, the good news is they will have some more work to do, and this may allow some competitors, new competitors, maybe. Second fly in the ointment for these guys is way more serious. Everybody is going to move to the cloud sooner or later. My favorite example is from Dave DeWitt. The previous speaker mentioned Azure. Here's Azure's data centers as they're currently deploying them. They are shipping containers in a parking lot. Chilled water, power, and internet go in, otherwise they're sealed. Roof and walls are optional. They're only there if you need them for security. Line up the shipping containers. They're sealed. If there's any failure, just turn that node off. When too many nodes get turned off, bring in a forklift, take the thing away, and replace it by a new one. If you think about raised flooring in Heidelberg versus shipping containers in the Columbia River Valley, guess who's going to be cheaper? So everybody's going to move there for cost reasons. And, AWS, mentioned by the previous speaker, plays by different rules than if you are buying hardware. So AWS gives you two different storage options, S3 and EBS. I'm not going to tell you what they look like. One is dramatically cheaper than the other for no good reason. So Amazon is not implementing economics here. They're pricing, in an arbitrary way. Also, they have a bunch of in-house solutions that they wrote. Redshift is one, Aurora is another, Spectrum is the third one. Amazon gets to choose how to price their internal software because they are running the hardware. All the other guys who want to run database systems on AWS have to rent resources from Amazon. Amazon charges, their charging algorithm for their internal systems dramatically favors in-house solutions. So it's not a level playing field at all. So that's kind of a problem if you want to compete against the in-house solutions. And even if you don't, Amazon has the notion of a t-shirt size, which is a bundle of resources that you can pay for. It has virtual CPU speeds, memory sizes, that sort of stuff. There's at least 50 of them with different prices, and you have to decide which one is the best way for you to compute. So cloud architecture is going to be a huge challenge for anybody who's going to run there, and we're all going to run there. However, this all is a blip in the overall scheme of things. The big problem with warehouses is that's yesterday's problem. So people have been predicting that data science will supersede business intelligence. Business intelligence is SQL analytics, data warehouses. Data science is going to supersede this stuff as soon as you all train enough data scientists to go out and fill all the open positions. So predictive models are great, and they're going to replace big tables of numbers. Data science is, of course, another meaningless word. It's whatever the marketing guys decide it means. So let me tell you what I think it means. Basically, it's complex math operations. Leslie Lamport's kind of stuff. Machine learning, clustering, k-means, predictive modeling, Bayesian analysis, all that stuff. That's what big analytics is all about. The world of the quants, rocket scientists. And the thing that is really interesting is that this is mostly specified as linear algebra on array data. And there are a dozen or so common inner loops. So let me just give you a quick example of why you should believe what I just said. So everybody's favorite example is the New York Stock Exchange. So consider the closing price on all trading days for the last 5 years of, say, Oracle and IBM. So the quants all want to say, I wonder if those two time series are correlated. If they're correlated positively, then if IBM goes up, then you want to buy Oracle. If they're correlated negatively, if IBM goes up, you want to short Oracle. Anyway, so obvious calculation is what's the covariance between these two time series. It's written down in the red. Go look it up in any linear algebra book. Well, that's not very hard. You can do this on your wristwatch. So to make it interesting, what the quants really want to do is do this for all pairs of NYSE stocks. There are about 4,000 of them. So 5 years worth of data is about 1,000 cells. So we have, for any stock, we have 1,000 closing prices of trading data. And we've got 4,000 stocks. So the red thing is a 4,000 by 1,000 matrix. So that's the data you get to deal with. And covariance, ignoring the constants, subtracting off the mean. What is it in sort of Leslie Lamport's terms? It's that red array times its transpose. Matrix multiply times its transpose. This is the inner loop of practically all complex analytics, is stuff like this. Now, the thing to get very clear is SQL is not going to do any of this stuff. First of all, SQL's on tables, not on arrays, and doesn't have any clue what stock times stock transpose would mean. So you can try this if you want to do something really hard. Try this in SQL with some relationalization of that red matrix. So this is what you want to do if you're into complex analytics. This is the rage in machine learning. Now I just want to point out the real rage in machine learning is deep learning, sort of big neural networks. They're really good at image understanding. They're really good at finding cats on the internet. They're good at natural language processing. This is not going to take over the world. This is absolutely not going to take over the world. So why not? Well, I'm involved in a startup that I'll mention later on. We do data integration. We have a big machine learning application. And it's conventional random forest techniques, machine learning as it's been known for 20 or 30 years. And we have a couple hundred customers, none of whom are interested in deep learning for this application. So what's the big problem? The big problem is training data. In the enterprise, which is where Tamer exists, training data means IBM SA is or is not the same thing as IBM Incorporated. So is the Spanish subsidiary the same thing as the US subsidiary? That's a yes or no question, but it requires your CFO to give you the answer. And so training data is invariably human approved, even if it's automatically generated. The high pole in the tent is getting enough training data to make any model work, and that's a struggle for all tamer customers. If you do deep learning, you need 1 or 2 orders of magnitude more training data, and enterprises are having a hard time getting enough just to do conventional ML. So in cases where training data cannot be automatically produced, deep learning is not going to go there. Also, right now, it's a little hard to explain deep learning predictions. If I'm predicting your credit score and whether or not you get a loan depends on the answer, then if you say your credit score is X, and I say, why did you say X? And you say, well, you know, this thing here said so. I mean, that will get you sued. So in a lot of real-world enterprise situations, you have to be able to explain yourself. And so far, that's a little tricky. You know, I'm sure the deep learning guys will get there, but they're not there right now. So there's going to be a lot of different machine learning stuff. Do not drink the deep learning Kool-Aid, at least not for all applications. So in this world of complex analytics, there's lots of ML platforms. I'm sure a bunch of you have used some of them. The thing I just want you to note is there's no data management and no persistence in any of this stuff. So you run one of your ML packages, it produces a bunch of output data. You want to save that output data because ML is an iterative process. You try it on different parameters and you get this sequence of stuff. You really have a workflow. And current ML packages are clueless on how to deal with persistence, workflow, and data sets over time. You can certainly run the stat packages. They also have weak or non-existent data management, same problem that the ML packages have. They use file system storage. And if you ever learn one thing from the data management community, is put your data in a database system, because then you can find it again. Do not put it in a file system and encode all the metadata in the name of the file. So anyway, I'm not a big fan of stat packages. There's a bunch of array database systems. Most of them are startups. If you have to deal with red data, why not use a database system that understands arrays instead of one that doesn't? So SciDB, TileDB, RasDemand from here in Germany, they're starting to get traction in the genomic space. We'll see how they do off into the future. Please, if you learn only one thing from what I say this morning, do not use Hadoop for anything. Hadoop is good. Hadoop is not good for anything. If you're using it, stop and do something else. And I can give you a long song and dance about why you're being stupid if you're using Hadoop, but I won't. So it's really the Wild West right now. So there's all kinds of stuff. It's a very immature field. There's lots of things that you would want. You would want a toolkit that could implement a lot of different algorithms, a toolkit that would remember everything you did and allow you to back up 3 weeks because you screwed up. Anyway, the goal is something that's wildly different than we have right now. It's the Wild West. Lots of interesting work to be done here, but this is not the 800-pound gorilla. I will come to that. Okay, so how about if your data is coming at you too fast? Well, sensor tagging everything of value, generates huge velocity. All the automobile insurance companies in the US are putting a sensor in your car to take note of how you drive. So if you jam on the brakes too often, your insurance rates are going up. They are reading that sensor, 30 times a second, times lots and lots of cars. Smartphones, state-of-the-art internet games, all of this sends velocity through the roof. So there's a lot more, big streams of stuff to process. So there's two different solutions here. If you want to look for patterns in a fire hose. So across the CNBC screen, you're seeing the trades on the NYSE, and you want to find out if Oracle is going up and within a short period of time, IBM's going down. So find me a strawberry followed within 100 milliseconds by a banana. There are complex event processing systems that are focused on this. Probably the most popular modern one is Kafka. Storm is another one. There are a bunch of proprietary systems. And I don't hear anybody complaining that these systems won't keep up with their problem. You could, of course, make them easier to code, use Leslie's technology, but I don't hear anybody complaining about performance. The other thing I hear is epitomized by a company called GetCo. You've probably never heard of it, but it's 10% of the NYSE trading volume day in, day out. It's an electronic trading company that has electronic trading desks in London, New York, Singapore, all around the world. And so the GetCo CEO is kind of nervous because all these independent trading engines can all decide to short IBM at the same time. And that will create way too much risk for the company as a whole. So what he wants to do, and what he's currently doing, is assemble for every security that they trade, some 60,000 of them, assemble my real-time global position. That means on a millisecond basis. And alert me if my exposure is greater than some tolerance. So that's his application. Now, if you think about this for a minute, you can't lose any messages. If you lose a message, this whole thing fails. If your hardware fails, then of course this fails. So this looks like high-performance online transaction processing. You want to update a database at very, very high rates of speed. So there's a bunch of things that look like this. So my suspicion is that there's more of these guys than there are people who want CEP, but we'll see. The commercial marketplace votes with its feet. So if you want to do this, you have three choices. You can run Oracle, the current, I affectionately call them the elephants, people who've been around for decades who give you what I like to call old SQL. Recently, there's a bunch of people who've alleged that no SQL was a good idea. That's 75 or so vendors, maybe 150. There's a lot of them. And their marketing strategy is you don't want SQL, it's too slow. And you can't afford ACID, it's too slow. ACID means transactions. So give up SQL and give up transactions and buy my software. So then there's a third camp, and the third camp has come to be called New SQL, which is these people say SQL is a good idea. High-level languages are a very good idea. Leslie just proved it to you. So SQL is a high-level language. The NoSQL guys say code and assembler. So SQL is a good idea, and by the way, transactions are a really, really good idea. But you can't use Oracle. It's architected, 20 years ago. So you need a new architecture. So if you run Oracle, forget it in this whole world. It's a couple orders of magnitude too slow. If you run a NoSQL system, and MongoDB is an example, Cassandra is an example, there's no standards, and by the way, if you want ACID and you're running a NoSQL system, then you get to code it in user space, and that is a pain worse than death. So I'm not a big fan of giving up ACID, giving up SQL, and certainly giving up standards is a lousy idea. So the new SQL guys are giving you main memory DBMSs, high availability, failover, stay up, et cetera, et cetera. They're running different concurrency control systems than the Oracles of the world. And there are a bunch of vendors here, all of whom will be happy to do 1 million transactions a second. And I don't know anybody who wants to go faster than that yet. So I view this as doesn't look very hard. So in the big velocity space, there's some people who want to do CEP, and products in the marketplace seem to work reasonably well. They could be easier to use, of course. And then there's next generation OLTP, which is a new class of database systems, and they are fast enough to deal with this market. So I don't see anything in the big velocity space that looks like an 800-pound gorilla. Okay, so where is, there's one fly in the ointment. Those of you who know about RDMA, it's a very fast way to communicate between nodes. The people who do this new SQL stuff may have to deal with RDMA, at which point they're going to have to rethink their their concurrency control algorithms. But they'll just do that. This isn't that hard. So where's the 800-pound gorilla? It's in the big variety space. So I want to tell you 2 scenarios. Scenario number 1 has to do with data scientists. So these are the people that we are trying to help with complex analytics, machine learning, all that stuff. So Merck, a big pharma company, has around 1,000 data scientists. Here's the template of what they do day in, day out. They have an idea. Does row gain cause weight gain in mice? I don't have any idea whether that's an interesting question or what the answer is. But it's just an exemplar of something you might want to know the answer to. So the Merck scientist has a huge data discovery problem. Merck has 4,000 or so Oracle databases. They don't even know exactly how many they have. They have a huge data lake plus all kinds of files, and the public web is a treasure chest of information. So just finding data sets that might answer this question is a huge challenge. And once you get them, then you've got to do data integration. You've got to put them together so that they can be, they're semantically the same. So here's a quote from the data scientist at iRobot. Those are the guys that sell you the self-vacuuming vacuum cleaners. So she said, I spend 90% of my time finding and cleaning the data, 90%. 10% is left for something else. So then she says, I spend 90% of the other 10% running my data models, finding out they don't work, and they don't work because of data cleaning errors, which is the input is too dirty to actually use. So she spends 99% of her time finding and cleaning data. 1% of her time doing the analytics for which she was hired. So those of you who want to make a difference, you can go help a data scientist with his algorithms. He spends at most half an hour a week doing that stuff. Or you can help him by helping him with his data integration, data finding problem. That's what he does 39 and a half hours a week. So this is the high pole in the data science tent, which is getting and cleaning your data. Well, the enterprise guys have a version of this, which is very compelling. GE, which is the guys who conglomerate who's been in the news a lot about whether their management is any good. So the GE CFO estimated that they can save $100 million a year with the following tactic. They have 75 procurement systems. So a procurement system, for those of you who don't know, is that if you work for a company and you need some paper clips, you go to your procurement system, it spits out a purchase order, you take the purchase order down to Staples, and you get your paper clips. GE has 75 of them. The obvious correct answer, using Leslie Lamport's notions, is 1. GE has 75 for all kinds of political reasons. So if GE can empower each of these 75 procurement folks, when their contract with Staples comes up for renewal, find out what the terms and conditions negotiated by the 74 other procurement officers, what they are, and then demand most favored nation status. That's worth $100 million to GE. Of course, what do you have to do? You have to integrate 75 supplier databases, because there's a supplier database behind each of these procurement systems. They're all independently constructed. And by the way, once you get done doing that, GE wants to integrate parts, customers, lab data, goes on and on. Okay, so the data integration challenge faced by GE and bunches of other enterprises, for every local data source, after you find it, you've got to ingest it, get it into some common place, perform transformations. You guys use euros, we use dollars. You've got to get the units to be the same. You've got to clean the data. That is an Achilles heel. A rule of thumb is that at least 10% of your data is either wrong or missing. And you've got to fix it. And then you've got to line up the fields. You call them wages, I call them salary. That's called schema integration. Then GE wants to find all the different records that correspond to Staples. That says deduplicate all of the data that you've put together. And sometimes you want to find golden values, which is, Dave Patterson, you've got 5 records for Dave. 3 of them say he's 46. 1 of them says he's 52. You got to decide, gee, they're all wrong. Anyway, that's what finding golden values is. Do all of this stuff. And the thing that is a killer is you've got to do it at scale. So GE has about 10 million supplier records. So running an n-squared algorithm on 10 million records is a not go out for lunch. It's take a short vacation. So you can't use an n-squared algorithm. We're here in Europe. It turns out Toyota is a customer of this company, Tamer. Toyota has an independent subsidiary in every country. Spain has one, France has one, and so forth. If you buy a Toyota in Spain and you then move to France, Toyota develops amnesia about you. The French guys have no idea what's in the Spanish database. So Toyota is in the process of integrating their customer databases all over Europe. There's about 30 million records in 40 different languages, just so you can get a sense for it. And do not think about naive algorithms in Python. This is a problem of making stuff perform at scale. So this is what you have to do. The traditional solution simply does not work. So the traditional solution is what's called extract, transform, and load. It's brought to you by a whole bunch of legacy companies. And it's been extended somewhat recently with what's come to be called master data management, brought to you by the same cast of characters. And extract, transform, and load requires way too much manual programming by a programmer. So it just is too expensive. And master data management simply does not scale to 30 million records. Why do I say it doesn't scale? Well, here's MDM says, master data management says, well, if I have IBM SA and I have IBM Incorporated, they're the same thing, match those, deduplicate them. So they're saying write a bunch of rules to decide what matches and how to merge multiple records into a single golden record. So they say do it with rules. So just a round number is that a human can grok around 500 rules. Nobody's written rule systems that work with 5,000 rules. You just can't get your head around them. So one of GE's problems is they have 20 million spend transactions. Spend transaction is Leslie went down to Staples and bought paper clips. So they got 20 million of those, which I think might be their annual spend in a couple of divisions. And their CFO just says, how much money are we spending on computers? How much money are we spending on travel? So they have a classification hierarchy of, of parts and then computers and then memory and so forth. So they have a pre-existing classification hierarchy, and all they want to do is classify 20 million transactions into this hierarchy. So they wrote about 500 rules, which is how much you could kind of get your head around. And that classified 2 million of the 20 million spend transactions. That leaves you 18 million to go. So far, this is totally useless. So you can't write 5,000 rules or 12,000 rules. The technology just is the wrong way to think about things. So the obvious solution here is you've got to use machine learning, statistics, to do as much heavy lifting as possible with minimal human involvement. So Tamer, the company I'm associated with, used the 500 rules as training data. That gave you 2 million labeled records. And they built a predictive model to basically classify the remaining 18 million. You've got to do it this way, or you've got to do something that isn't a rule system. So anyway, this is a hugely important problem. Hugely important problem where the traditional solutions do not work and are known not to work. So there's lots of startups in this space. It's the wild, wild west. Hold on to your seatbelt. But remember that if you're interested in data science, this is the important part of data science. It's not data science. So if I was you guys, I would work on this stuff. So anyway, in summary, machine learning will be omnipresent, absolutely omnipresent. Some of it will be deep learning, some of it will be conventional ML. Complex analytics is going to replace data warehousing as soon as we can get enough people to understand the stuff. And both ML and complex analytics are going to go nowhere without good data. And good data requires data integration at scale, the 800-pound gorilla. So this is the high pole in the tent, in my opinion. And what I think I'd like to just leave you with, if you want to really make a difference, think about working on this stuff. And I'm done. Thank you.
Okay, given when we started, I think we have about 5 minutes for questions. Let's see if we have questions from the young people first. There's one. Should I be running with this mic, or you're running with the mic? Okay.
Okay, thank you very much for the presentation. At the beginning of the presentation, you explained the meaning of big data with the 3 V's, the big volume, big velocity, big variety. My question is, at what point in time can you describe your data to be big, such that it has a big volume, big velocity, and then big variety? Thank you.
Okay, so what exactly does this mean when you're down in the trenches? The answer is you have a big data problem if you're tearing your hair out trying to get your application done. And that isn't specifically number of bytes. It's how much pain are you in? And if you're in a lot of pain, you have a big data problem.
Hey, another question from the young folks? Come on, people. Okay.
Hi, Mike. Thank you for your talk. First of all, I'm very surprised that you're not wearing one of your red signature shirts.
I was told by the organizers that I had to dress up. So.
Oh, okay.
This is as dressy as it gets.
All right. No red shirt this time. The question is whether you think it may be possible that at some point we will develop analytics algorithms that won't need clean data because they will be robust to all the error in the noise model that, the noise that may be added by the human in the loop or whatever. I mean, statisticians have worked with sensor data and with missing data for a while, multiple imputation and stuff like that. Surely their algorithms are not scalable yet, but I mean, we can move to robust machine learning, robust analytics that won't need such an expensive data cleaning step.
Okay, so here's my problem with that. The question is, why can't we build super smart algorithms that tolerate dirty data? The answer is because you can't tell it's dirty. Is IBM, IBM SA and IBM Incorporated either are or are not the same thing. If they're the same thing, then your algorithm goes one way. If they're different, then your algorithm goes a different way. Only a human can tell you whether they're the same or not.
Only a human can recognize cash.
All true also.
This can't be true.
Say.
Mic, but I'm going to give him a mic anyway.
Or to ask the question another way, what are you actually doing when you're cleaning data?
What are you doing with your clean data?
When you are cleaning your data?
How
do you clean your
it?
data? Why are you so sure that a machine can't do it?
Well, I agree. What happens is there's you can use outlier detection, you can use functional dependence, there's a bunch of stuff you can use. That gives you a collection of things that you think might be dirty. And if multiple of these algorithms think it's dirty, then chances that it's dirty go up. So then you say, well, how do I fix it? Well, automated repair is in its infancy. Now you can say, well, maybe ML can do that. But the trouble is you're then going to have to check the ML, and that's the big problem, because then you're back to the human in the loop, as the high pole in the tent.
Butler looks skeptical, but we will go on to the next question, which will also be the last question. There was a hand in the back. Maybe somebody could.
Hello. I'm Don from Technical University of Berlin. So I work a lot on sensors networks, so sensors were getting really cheap. Do you think that online collecting data compensate to the cleaning problem because other source data can help to fix other problem in the data?
Well, I'm just saying that your data, 10% of it is wrong. And so if you're going to launch a nuclear missile based on your current data, I wouldn't do it. I'd clean your data first. Now, if you don't care about data, about accuracy, then by all means do whatever you're doing. But I think the answer is people, at least in enterprises, there are a bunch of Tamer customers who say, how many suppliers do I have? And it really makes a difference to how they think about things if the answer is 50 versus it's 1,000. And dirty data is the difference between 50 and 1,000 typically.
Yeah, I agree, but somehow that if you have more data that you will spend less effort in cleaning and the problem is getting smaller.
Okay, I think we should take further discussion during the lunch break, and let us thank Mike for the very insightful lecture.